Okay, welcome back, and we will continue our discussions on thermal management analysis and design, which is a very important module of this course on electronic packaging and manufacturing. So, in the last couple of lectures, we kind of revisited the concepts of heat transfer and also solved a couple of problems applied to the domain of electronic packaging and cooling, rather electronic cooling. So, today and that was primarily about heat sinks, which is probably the most common heat cooling solution that is used in electronic products. Today we will look at, apart from heat sink, what are the other thermal technologies, some other thermal technologies that have been used. Okay. So, that is the concept that is going to cover today, that is going to be covered today, thermal technologies. Okay. So, let us move on and look into the first one, which is called cold plate. So, there is a heat sink through which this primarily air cooled heat sink is what we talked about. But what is a cold plate? Cold plate is, instead of air, if you are having a liquid coming in. So, then the liquid, as it flows over the CPU through this cold plate, it picks up the heat and that is generated at the CPU, and when it leaves as a heated liquid. Okay. So, this is a typical picture of a cold plate. Okay. Of course, the cover has been made transparent, because if you look from outside you will not be able to say that, you will only see an inlet point, an outlet point, and probably a copper or aluminum block, but inside you have this serpentile channels. Okay. Serpentile is one configuration, you can also have parallel channels, right. If I have to draw it here, you can have a cold plate with parallel channels like a heat sink, and then what is called an inlet and exhaust manifold. So, the liquid comes in and then gets distributed, and then again it comes out. Okay. All right, and on the right hand side what you see is typically a simulation which tells you how the temperature of the fluid varies. It comes in, so it is blue, so it comes in as a cold liquid, and then as it flows through this serpentile path and picks up the heat and therefore gets heated itself, it leaves at a higher temperature. So, okay, and that is the change in color gives you that variation. All right. Now, what do I do with this heated liquid? In a heat sink, the hot air is thrown out. In our laptops, desktops, everywhere, in TVs also, you will see this. In many of these electronic appliances, you see this. But liquid I cannot just throw away. So, therefore, any liquid cooling solution, cold plate being one of them, what you have is, it is called a pumped liquid cooling loop. So, definitely, like you have a fan for air cooled heat exchanger under forced convection, you need a pump for liquid cooling. So, if it is water, you need a pump that forces the water to flow through this cold plate, and then this coolant, it comes out in the form of hot liquid as we saw, and then what do I have to do? I have to cool it down using this air cooled radiator type heat sink or heat exchanger here. So, therefore, this coolant at a higher temperature, the liquid at higher temperature flows over, and then you have these fins attached to the outer surface of this tube or pipe, and you have a fan blowing air to extract the heat. Okay, this is a typical heat exchanger, a water air or air water heat exchanger, and so therefore, the liquid gets cooled back and is again ready to be pumped in to the cold plate. Okay. So, therefore, the heat that is extracted out of this by the liquid is again dissipated at this heat exchanger, and the liquid is cooled down. So, the next question that you will ask is, so finally looks like everything is air cooled, right. So, the liquid just helped in dissipating the heat from this point, in extracting the heat from this place of generation and transferring it to this place where it was eventually air cooled. So, the question is that why not put this heat exchanger or this heat sink with the fins and the fan right over here. Okay. Why? In fact, this actually adds a little bit, whatever, however tiny that is, it adds to the overall thermal resistance, because these are in series, right. There is a convection resistance for the liquid, and then there is a convection resistance because of this air cooled heat exchanger. If you had put the air cooled heat exchanger directly on the CPU, you would have been able to reduce the heat thermal resistance. Why did we not do that? That is because, look at this, this is a real sample. Look at the size of the heat sink or heat exchanger, look at the size of the fan, and look at the size of this cold plate which is here with this inlet and exit. So, the cold plate is required because I do not have enough space at the place where I need to cool. Okay, that is why the cold plate is required. And of course, there are other advantages of liquid cooling as well. Of course, there are disadvantages as well, this pump reliability, it is a more complex system, but the advantage is this part, the heat exchanger part, can be away from these circuits and components. So, all the problems about vibrations because of the fan running at certain few thousand RPM, because of dust, etc., will not be there. Okay. So, this is called remote cooling, and the liquid, all it does is it helps in conducting the or transferring the heat that is generated from this inconvenient location to this convenient location where it can be air cooled. So, finally, everything is air cooled. If somebody says I will replace air cooling by liquid cooling and get a lower thermal resistance, the immediate point you will ask is, come on, you cannot do that, because finally you have an air cooled, you must have an air cooled heat exchanger, unless you are saying that you can dump the heated liquid somewhere. Such applications are very, very few. Maybe if you have some underwater electronics, maybe during deep sea drilling and all, that is possible. Probably you can have a liquid cooled loop, you have a lot of sea water around, and yeah, liquid cold water comes in, hot water is just dumped into this large volume of the ocean. That is one example, but otherwise no. Okay. So, otherwise everything is finally air cooled. The other thing I want to point out is, both, I mean, in here as well as in the previous one, I said cold liquid in, heated liquid out, but there can be situations where the liquid may reach its boiling point and start to boil, and therefore, what comes out is liquid plus vapor combination. Okay. So, that is also possible, that is called two phase cooling. The heat transfer coefficients in two phase is very, very high, but so is pressure drop. So, therefore, the pumping power that you need for two phase flow is very, very high, but so will be the heat transfer coefficient. So, therefore, this part will be very, very small. Okay. The next one I am going to talk about is something called heat pipe. So, heat pipe is a thermal solution that is used in laptop computers. I think almost all laptops have heat pipes. Laptops that have fan heat exchanger inside have heat pipes. So, it is very similar to liquid cooled, except that you do not have a pump. But before that, so this is the die, there is a thermal interface material and there is a cold plate, or there is a thermal plate, let us say. Okay. So, this is where the heat needs to be extracted, but then and finally rejected to the environment using this fan and heat sink, this blower and heat sink, parallel plate heat sink. But then the size of this fan and heat sink, just like liquid cooling loop that we saw before, is too large to be kept at the CPU location. So, what do we do? So, we put something called a heat pipe. From outside it looks like a copper rod, but you know what happens inside? It is actually a hollow tube with a fibrous material attached to the wall in the annulus, which is called the wick. So, what happens is, one end of the heat pipe where when it is heated, the liquid starts to boil. Okay. As the liquid starts to boil, it converts to vapor and flows through this central core to the other end, where you have a means of extracting the heat out, maybe through a fan heat exchanger like this. So, where the liquid, the vapor or the fluid gets cooled and the vapor condenses back to liquid, and then the liquid is pumped back to the hot section because of what is called the capillary action inside the wick. Wick, remember, when we light the diya at our homes, what do? The diya has some oil and then we have this wick, it is cotton, and you light the fire at the tip. And what happens therefore is that the oil percolates through the wick to the tip where it is lighted because of this capillary action. It is exactly the same thing here. It is a fibrous material and which helps in driving the liquid back due to capillary action. Okay. So, this is like a liquid cooling, two-phase cooling, but you do not need a pump because the pumping action is accomplished through this wick. So, I have a sample over here. Okay, once again, as you can see that the heat pipe is just a method of transporting the thermal energy from this location where it is generated to the point where it is rejected. Finally, it is air cooled. Okay. So, I have a sample which I want to show to you over here. If you can focus on this screen, see, this is a typical heat pipe heat sink arrangement in a laptop computer. Okay. So, this is this plate inside which this heat pipe is embedded. This is what sits on the CPU. Okay. And then this is a fan and this is this parallel plate heat sink. I am sorry, this has got a little damaged at the ends. Okay. So, therefore, what happens is the fan blows air through this heat exchanger or through this parallel plate heat sink. All right. So, here it shows two heat pipes, but in most cases there can be one, and rather in most cases there is one. Okay. All right. Again, there is no standard design because every layout in the laptop is different. So, therefore, whether the heat pipe is going to have a bend or whether it will be straight or whether it will have two bends, whether there will be two heat pipes, whether it will go on the fan casing like this. I mean, these are all they are pretty non-standard. These are from one model to another, it will vary, but the basic principle of a heat pipe heat sink arrangement is the same. So, this fan blows air. Okay. As it is powered on, the fan blows air through this heat sink, and that is how the heat is rejected, extracted from here, transported to here and rejected. All right. So, from outside what do we see? This looks like a copper rod, right, a flattened copper rod, but actually inside it is hollow. All right. So, let us come back to the screen. So, why do we use heat pipe instead of a copper rod? Because the effective axial thermal conductivity is very, very high. It is like 10,000 watts per meter Kelvin. Copper is 400. So, this is a much more efficient conductor. Okay, conductor within quotes, because it is an effective heat conduction. Actually, what is happening inside is a very complex heat and mass transfer phenomenon. Okay, it is two-phase flow. Now, what do most of these heat pipes have? What is the liquid that is used? It is typically water, a few drops of water, but the pressure inside is lower than atmosphere. So, that is why the heat pipe is evacuated and then sealed at the top. So, let us see, if I evacuate it to around 0.3 atmosphere, then the water will boil at 70 degrees, because otherwise if it is atmospheric pressure, the water is not going to boil before 100 degrees C. Clear? All right. So, that is the heat pipe. Refrigeration cooling techniques. What if I want the temperature of the CPU to be lower than the ambient? Can I remove heat from a lower temperature to a higher temperature? The second law of thermodynamics says you can, only if you do work on the system, if you spend energy. So, that is refrigeration, moving heat or heat flow across an adverse temperature gradient from a lower to higher temperature, and that is accomplished in our ACs, in our refrigerators, that is accomplished by the compressor, which needs external energy. Okay. So, a refrigeration system has an evaporator, okay, which extracts heat, and in case of electronic cooling from the CPU, in case of your refrigerator from the chamber inside, in case of your air conditioner from the room. Then the refrigerant comes out in the form of vapor. It vaporizes actually. The refrigerant that flows through this evaporator comes in as a liquid and comes out as vapor, and that vapor is compressed. So, as a result of which what comes out of the compressor, the refrigerant vapor, is at a higher temperature and pressure, and then the heat is extracted in the condenser, which typically is situated outside the main refrigerator chamber or outside in the outside unit of your room air conditioner. Okay. So, what comes out of the condenser is therefore again refrigerant liquid at the high pressure and therefore high temperature as well, typically ambient temperature, outside ambient or slightly lower or sorry slightly higher. And then what we have is something called an expansion valve, where it undergoes a sudden expansion, a large pressure drop, and as a result of which the refrigerant vapor cools down and also expands to a lower pressure. And so, what comes out here again is the refrigerant liquid or a mixture of liquid and vapor at a low pressure and temperature, and this is how the circle continues, extracting heat from the evaporator section, rejecting heat out at the condenser section. So, for CPU, I am going to place this evaporator on the CPU, which is generating the heat. All right. So, similar another refrigeration technique, which is known as a solid state refrigeration, is known as thermoelectric refrigeration. A thermoelectric cooler or thermoelectric refrigeration, by the way, thermoelectricity, as the name suggests, is thermal and electrical. Okay. It can work both as a generator of electrical power, or given an electrical power, it can lead to a temperature difference. So, what we are going to talk about is as a cooler, where we are going to supply electrical power to this thermoelectric cooler, and as a result of which it is going to cool down. So, a thermoelectric refrigerator or thermoelectric cooler consists of an array of semiconductor devices, where you have what is called a Peltier couple. This, by the way, this effect is also known as Peltier effect, and Peltier cooler is also a term that is used after the person who first came up with this, invented this phenomenon. Okay. Seebeck and Peltier, we owe it to them. Okay. They are the first who showed us that if two dissimilar materials or conductors are joined at the two ends and electric current passes through, a temperature gradient will exist. Or what Peltier said is, if you want to keep them hold the temperatures at a certain level, heat has to be extracted out from one of the ends continuously. That was Peltier effect. Seebeck effect, on the other hand, says that if there is a temperature difference, you are going to it's going to give rise to an EMF or a potential difference across the two ends. Okay. So, Seebeck is one which the Seebeck effect is used for generation, Peltier effect is used as cooler. But okay, we can do all those. I mean, you can read this up separately. But what a Peltier cooler has is, it has a pair of a p type and an n type semiconductor, p doped and n doped semiconductor. The p one has more number of holes, n one has more number of electrons. These are the free charge carriers. Okay. So, now if we pass an electric current through these, okay, the other thing is, these are kind of arranged such that they are electrically in series. So, as you can see, they are connected at this end by a conductor made of copper or some other conductor, and then thermally in parallel, in the sense the top surface has a certain temperature, bottom surface has a certain temperature. So, if there is a temperature gradient that exists between the top and bottom, there will be heat flow in one direction through this p as well as n type, and they will be treated as parallel heat paths. Okay. So, now what it says is, if you actually pass an electric current through this, then there will be heat absorbed at one end, and in order to keep this at the same temperature, if you reject it, you have to put a heat sink and so on, and dissipate that heat out. Okay. So, that is my thermoelectric cooler. All right. So, now what we will do is, this is a broken down view, because there are lots of these p n junctions and then this is how it actually looks out from outside. Okay. What we will do now is we will look at a small video which kind of explains how thermoelectric generator works, at least in the first part. It will talk about both generator and cooler. So, this is from a company called Marlowe, and you see this P and N type next to each other. Typically, they have a ceramic substrate, but you see this conducting copper interconnects at both ends. Okay. So, this can be used for cooling, which is what we were talking about. It can be used for heating as well if you change the direction, depending on which end is of interest to you, and it can be used for power generation as well. So, you see alternating P and N type next to each other, wired electrically in series, and then also in series like this, and thermally in parallel, assuming that the temperature difference is between the top and bottom surfaces. Okay. So, depending on which direction the current flows, it can be used for cooling the top one or the heating the top surface. So, if there is a temperature difference that is imposed, you can also generate electricity. So, it is the other way. In the first one, as a cooler, we were actually putting in electric power and we were getting this temperature difference. On the other hand, in case of a generator, if you actually have a temperature difference, you can use a thermoelectric a Peltier device like this to generate electricity. Okay. I think rest of it is fine. So, generation of electricity, for example, if you have waste heat somewhere, okay, let us say that you have a lot of steam or a hot surface which otherwise you are just wasting its heated temperature, and on the, so if you can now put one of these Peltier devices and put a heater at the top and the other side is maybe kept on a cold surface, you will be able to see that there is an electric flow of electric current through these wires. Okay. So, thermoelectric generation is often used where you have a lot of waste heat, for example, exhaust of a car battery. Okay. Can you put some of these thermoelectric coolers at the exhaust pipe, right, because in the inside surface through that pipe you have very hot gases at 600-700 degrees C coming out. The other side is probably, well, more than ambient, but probably within 100 degrees or so. So, there is a large temperature difference and that can give rise to electrical. So, that the temperature difference can be leveraged using this thermoelectric effect to generate electric power. But for our case, for refrigeration, we are looking at it as a cooling device. Okay. So, once again, just to wrap up in this lecture, what we discussed is we started with of course, in the till the previous lecture we talked about heat sinks, and then at the beginning of this lecture we said, okay, heat sink is typically air cooled. When you have liquid cooled, we typically call it a cold plate. We saw a cold plate with the serpentine passages inside, but again the point I wanted to make is a liquid cooled solution will almost always have to work in a closed loop, whereas the heated liquid that exits the component that is cooled or exits from the cold plate has to be cooled back using a remote heat exchanger and then pumped back into this cold plate. So, therefore, finally everything is air cooled. It is just that I am unable to put that air cooled solution for some reason, most likely for space constraints, at the location where the cooling is required, or so therefore, I have to extract that heat and transport it to the location where it is cooled. Okay. So, that is cold plate. Next we looked at heat pipe, which is a similar device used it is almost ubiquitously present in all laptops, and we also saw a physical sample of that. Here the heat pipe is also a mechanism to transfer heat from the location of the CPU to the location where I can put a fan and heat sink. But the heat pipe, from outside it looks like a copper tube, but inside there is a lot of complex two phase flow that is happening. There is evaporation or boiling at one end, condensation at the other end, and this is a pumpless system because the pumping of the condensed fluid back to the hot section, which is also called the evaporator section, is because of capillary action through this porous or fibrous wick material. Okay. Then we talked about refrigeration systems, and finally we talked about thermoelectric refrigeration, which is a solid state refrigeration. It does not need compressor. Okay. So, no moving device. It comes at a very small, it is coming at a very as a very small piece, maybe 2 inch by 2 inch. But the problem here is for thermoelectric, it is an extremely inefficient device. Okay. In a refrigeration, in a proper refrigerator, which is also called vapor compression refrigeration cycle, which is what is used in our refrigerators and air conditioners, the amount of the ratio of the amount of energy that you have to spend to run the compressor to the amount of heat that you can extract from the place you want to refrigerate, that ratio is also called coefficient of performance. That coefficient of performance is much higher for a household refrigerator or air conditioner, or for a conventional vapor compression refrigeration system. It is very, very low for a thermoelectric refrigerator. So, which means that you have to spend a lot of energy. The amount of cooling that you are going to get is going to be a much lower for the same amount of energy that is spent. So, therefore, you do not have a fridge or a room air conditioner based on thermoelectrics, but for localized thing, where you have space constraint, you just want to put something, or then this is for localized cooling, where the amount of electrical energy to be spent is not a lot, even though the amount of cooling that you are going to get is going to be low. We use thermoelectrics, okay, because of its convenience, of its reliability, because there is no moving parts, no noise, no vibrations. So, that way it is very, very convenient, very, very nice, very, very elegant. Okay. Actually, there are some small small refrigerators that can be used for medicinal cabinets in clinics. So, these can all be used based on thermoelectrics. All right. All right. So, thank you very much. That is all I had for this lecture, and when we come back in the next lecture, we will talk about some of the more a little bit of this novelty and some innovative solutions that have come up, some not the obvious ones like water cooled, air cooled, even refrigeration or thermoelectrics, which are now pretty well known, but we are going to look at some of these more novel cooling technologies that have been, maybe a few of them that have been explored and researched over the last few years. Okay. Thank you very much, and see you in the next lecture.